Hey guys, welcome to gymterm2b walkthrough. Hopefully you guys have seen the first one, 2A, and that's helping you guys out. Again, I know it's a little rushed, it's just because there's so much material. So there are those extra videos to help you guys out. There's two EAS videos, the ones with EAS kind of highlighted in the name. It's because the first one is like 2 hours long, but the second hour actually got cut off, which is kind of tragic. Or like the last bit got cut off in audio, which is a bit tragic because that's what the second one is for. And then there's the aromaticity video. So you can watch those if you need extra support. Yeah. So you can go ahead and watch those. I think the most relevant portions, maybe if you were stressed on time or if you wanted to focus on certain things, I would like for EAS wise, I would only watch the second video because that goes over directing effects, whatnot. And so it's like the most important thing on this exam in terms of benzene reactions. So cool. But yeah, I think I'm also just going to go over both exams in this video. We'll just do our best. I'll probably just speed run through this one. So we'll just be mostly just answering questions and talking very briefly about concepts, stuff like that. Just so we have everything down. Because, again, I don't have much time to do much more. Cool. All right. So let's just get right into it. The goal for today is an hour and a half. So again, watching the clock like a hawk. But let's go. So which of the following compounds reacts fastest with bromine and iron? Oh, that should have been tribromine. That's my bad. But essentially it's right. It's just the question is just this: X2 and metal X3. Which benzene reacts the fastest? Remember, these are electrophiles. So benzene reacts with electrophiles, which makes the benzene itself a nucleophile. So if I want to increase nucleophilicity, right? I need electrons. So I need electrons. So that means I need activators, right? Or lone pair or any type of electron donor. So EDG type groups. Okay. The best being nitrogen lone pair, followed up by oxygen lone pair, followed up by R group induction. Okay. So these are our best. Halogens again, right? Remember those guys are actually deactivating overall rate wise. They're slower than benzene, but they do have lone pairs that serve as a quote unquote like EDG, right? But they would be the slowest out of these guys here. Okay, so technically these are activators. This here is actually a deactivator. So these would we really wouldn't want to choose this unless it's absolutely the best one. Okay, so any meta directors or any meta directors for sure, just get rid of them instantly, right? So meta director. I see. So this ring again, don't let it fool you. If you want to, you can even just split it up. You can just do this. Yeah, just do that and think about what effect does each of these groups have on the adjacent ring. Clearly, right, this carbonyl is deactivating the ring. This one's donating in inductively. There's a deactivator, so I'm just going to assume that's probably the worst or one of the worst, right? So what that leaves us with then is these two here. And so again, we have a bromine lone pair, and then we have two oxygen lone pairs that are conjugated to the ring. I'm going to go with the oxygen lone pairs as the best one. Okay, cool. So that's going to react absolutely the fastest with the electrophile. And again, the electrophile could be anything, right? Doesn't really matter. The identity of the electrophile is not key. What's important is, if it's an electrophile, what does the benzene need? It needs electrons. So we want EDGs. So that means that the slowest then would be probably this guy here, right? Because there's two EDGs on it. Oh, sorry, two EWGs on it. Especially NO2, one of the most powerful EWGs in the world. Cool. All right, so we'll call it on there. Actually, let me check something. Did I ever ask this question? I guess I did it. So this is, I guess I should have asked this, but you could also be asked between, who reacts the fastest with any type of electrophile, where you have like benzene, you have a conjugated diene, maybe you even just have a diene or like an alkene. And then actually we could even do this. So imagine if you're asked this question, where you're asked, which of these rings reacts the fastest with some electrophile? Let's just say Br2, right? Who would react the fastest? Okay. Now, very, very common thing mistake people make is they, again, associate certain topics or not necessarily associate, they kind of memorize certain topics with certain structures or certain, certain molecules. For example, a couple of you guys might even just see A and think, okay, anytime I see EDG on a ring, I want to think that that's always the fastest. Sorry about allergies for some reason, which I can understand why you think that, especially when comparing benzenes, that's the case. But when we're comparing other alkene species to benzenes, right, we have to remember one thing. Generally speaking, a benzene is pretty stable, right? Like if I have a benzene, that thing doesn't want to react anyways. It's a very, very stable molecule. In fact, remember, if I have like an EDG, like a nitrogen, so let's say I have a nitrogen, right? Who's the atom that reacts the fastest usually with electrophiles? If I have like a free aniline just like that, it's not the ring, right? The first thing that reacts is the nitrogen. So when we think about which alkene reacts the fastest, generally speaking, benzene alkenes are going to be slower than most alkenes on the market. Okay, so these guys are going to be actually lower. Like I can do NH2 and NO2, right? These guys are going to be on the slower end than these two over here. So, I mean, obviously this guy's going to react faster than the EWG. So this could be like 3, this could be like 4, where 1 is the fastest and 4 is the slowest. Okay, so that would leave us with these two guys here. Okay, cool. So hopefully that makes sense. Benzenes, again, benzene alkenes usually slower than normal alkenes. Okay, now let's say that I also, have these guys here, the alkene and the diene, who should react faster. One very common thing people think, and makes sense why. So don't feel bad if you thought this. It makes total sense why you would think this. You see the alkene and you see the diene, you think, okay, the diene is more stable. That is true, right? Because it's conjugated. It is more stable. So that must mean that its reactivity is lower because stable things don't like to react. If you thought this, then you are thinking correctly, right? Or at least you are thinking with the tools that we have given you. But one of the craziest things when it comes to thermodynamics, when it comes to reaction mechanisms, when it just comes to organic chemistry in general, stability often rarely correlates. I mean, it doesn't correlate very well with reactivity. Now, most of the time in this class, it is engineered such that when you think stable, you can think less reactive. But let's think about the intermediate of either one of these reactions. Okay, so if I have the intermediate of this guy here, it would be this secondary cation here. Okay, and if I think about the intermediate of this reaction here, right, it would be this allylic cation here. Which cation is better? Right, clearly, I mean, if both of them are secondary, the one that's gonna be better is the one that's allylic because it can also resonate. So generally speaking, this cation here is a bit more stable. Not even a bit, it's quite a bit more stable. It's a lot more stable. Okay, because this cation is more stable, right, we can reasonably assume that forming that cation is going to be a lot easier than forming the secondary cation here that can't resonate. So almost counterintuitively, despite the fact that this diene is more stable, it actually reacts a lot faster than a normal alkene. Simply because this allylic cation is super easy to make, right, compared to just a normal secondary cation. Remember back from 118A, or if you don't know, I'll tell you now. Secondary cations already kind of suck, right? It's already pretty hard to make them. So if they're allylic, you've kind of boosted the ability for it to exist, right, to even sustain itself in this environment. So in fact, actually, the fastest reaction alkene is going to be the diene alkene. Okay. One way to think about this is that, remember, the diene alkene, I've been seeing this a lot, is that a lot of people are treating diene reactions as, looking at which alkene is quote unquote more nucleophilic. I've been seeing this quite a bit, and I can understand why. That's kind of the way you guys have been taught. A lot of you guys have been looking at this and thinking, okay, this methyl here, right, on this alkene, that must mean that this alkene is always going to be more nucleophilic as the one that's going to attack. Remember, dienes are conjugated. They are sharing their electron density. So really, the most accurate representation of this molecule is going to be the one where this is dotted, right? So it's really going to be this. Oh, sorry, not that. Oops, this. Right, this is the most accurate representation of the molecule. The alkene electrons are not localized, right? There's no discrete pi bond at any position. It's completely delocalized. So at any one of these positions, right, technically any one of these positions, the alkene electrons could attack, right? The diene electrons could attack. What determines which position attacks is going to be the one that results in the most stable allylic cation. Right, that's always the key. So whether we attack from here, whether we attack from here, or from here, it's all a function of where is the most stable allocation going to form. Okay, or which one's going to promote formation of that allocation. So remove this idea. Remember, dienes are different from alkenes. If they were the same, we would have introduced them back in chapter 12 and called it a day. Right, we would have done that, and we didn't because they are slightly different, right? They have a little bit different mechanics involved in them. Okay, cool. So they are more nucleophilic, generally speaking, just because also they just have a lot more electron density to them. Okay, cool. So if I wanted to order these, right, it'd be 1, 2, and then 3, and then 4, just like that. Okay? And it's any electrophile. I guess if you wanted to make an electrophile that makes sense, right? You do like Br2 because that's something that can react with benzenes and alkenes generally, right? Although with the, I guess you need some kind of activator, right? Like the metal for these cases here. Okay. Cool. All right. So we'll call it on that question there. Hopefully that was insightful. Cool. All right. Which compound is the weakest acid? So we have all these guys here. Again, remember with these acid questions, don't get tied into just, which one is more allylic and which one's less allylic. You have to also consider that possibility. There are the possibility of aromaticity types, some sneaking of aromaticity. So look for those rings that are fully conjugated when they're anionic. So I'm just going to be lazy here and just do this. And are any of these rings fully conjugated, right? Looks like these and these are. So they have the ability to be aromatic or anti-aromatic. Just a matter of counting pi electrons here. So 1, 2, 3, that is 3 pi electrons, or 3 pairs of pi electrons. So that'd be 6. So this is aromatic. This is also aromatic. And then this is 8. So this is anti-aromatic. And then this is non-aromatic, right? Because it's not fully conjugated. So I know the question did not ask to tell me whether it was aromatic or not. But once we have these on the page, right now we know which one's going to be the best ones, which are going to be the worst ones, right? Remember, generally speaking, in terms of forming the anion, right? If you become an aromatic anion, so if you're becoming aromatic, you're the most acidic. If you are non-aromatic, right, you're about middle-ish, and then anti-aromatics are the worst. Okay, so very key important thing: you are becoming aromatic. So when is this not a case? Let's say that I have a pyridine here, which is just if I take a benzene and decide, okay, I don't actually, I want to be a little quirky. I want to make one of my carbon atoms with nitrogen. That's what pyridine is basically. And I decide to deprotonate on this position here. Right. This would be an example of an aromatic molecule that deprotonates that's still aromatic. This lone pair doesn't change anything. So the pKa of this is equivalent to any vinyl proton, really, in the 40s. So it's not anything crazy, right? But when we look at these two here, these are non-conjugated that become conjugated as a result of deprotonation. So they were not conjugated, and then it became conjugated to become aromatic. So that's the difference between an aromatic anion, right? It's when the lone pair directly contributes to the aromaticity. Okay, but in that case, right, these two are probably going to be the strongest acids. It's a matter of who's going to be more stronger, or stronger, I guess. We have a carbonyl here that can delocalize, stabilize charge, and we have our group here that donates and can interrupt the charge. So generally speaking, right, this is going to be the best acid. This is going to be slightly worse than that. Then we have a non-aromatic that's clearly going to be 2. Because it's not aromatic, and then we have an anti-aromatic that's not going to want to deprotonate at all. In fact, I believe the tropylium or the tropyl anion, when it does form, right, purposely forms like a little bridge, just to oh, I didn't draw that right. Yeah, there we go. It purposely forms a little bridge here, like a little TP, just to prevent conjugation, right? Just like the boat. If you guys remember the boat, cyclooctatetrene, right? Cyclooctatetrene reacts like a regular alkene, like a normal alkene, because it's completely non-conjugated, right? Looks like a very sad person. Cool. All right. So call it on that question there. Label the following molecules aromatic. Yeah. So remember, always go through your criteria. There's a couple of them. Ring, conjugated, planar, and then Huckles, foreign +2. I'll tell you what, I might have mentioned this on the last video too. Usually it's these two. It's these two that you have to figure out. Like those are the hardest ones because most things you can tell if it's a ring or not just by looking at it. So all these are rings. So obviously this is not going to help us. And most things you assume are planar unless you're told otherwise. So one of the things you're told, two of the things I will tell you is that this one here, right, despite appearing aromatic, is actually not conjugate. This is not planar, right, because of those clashing hydrogens in the middle. And then the other one is that the one we just looked at, cyclooctatetrene. Right, that's not planar either. Okay. But most things, right, you're really asking the question of, is it conjugated and does it follow foreign +2? So we can do that for all of these. P orbital. I mean, so one trick that I always teach in the aromaticity videos is, anytime you see a pi bond, there's a p orbital, so you can mark it really quickly. right? And then if there's an anion, cation, a radical, just assume for the time being that there's a p orbital there, just to see if it's conjugated at least, and this is conjugated, so that passes the conjugation test. We'll come back to talk about this, but I mean, if we kind of go through this idea, right? We have p orbitals here because they're just pi bonds, and then we have a lone pair on the sulfur, so we can assume there's a p orbital there. Multicyclic rings are a little tricky when it comes to aromaticity. Borane counts as a carbocation, so we can assume that there are p orbitals there because carbocations have p orbitals. And then nitrogen, right, has those lone pairs, so can assume that it does. And then here, right, that carbon there is the trick. A lot of people see this nitrogen, instantly think it's part of the ring, just because they associate it, but it's not, right? That carbon is sp3. It's a roadblock. So unfortunately, this is non-aromatic. Not unfortunately, actually, this is it's non-aromatic. This is a good thing. We can just get out of the way. Yeah, cool. Now, actually, come back to the first one. We have a radical here, which means that when we do our pi electron count, the number is not going to even out very well in 4n plus 2. I'll tell you what, anytime you see a radical, non-aromatic. Okay, so easy, boom. So that just leaves these two in the middle here. We'll do this one first. So this here, I know it looks crazy and looks kind of scary, but you can kind of, again, assume that the boranes are carbocations, which if you do that, you'll notice that you can actually resonate the electrons from the nitrogen into those positions to form something like this. And what you get out is a triazine, okay, 1,3,5 triazine, which if you kind of look at it, kind of looks like a benzene atom, right? Where we just replace carbons with nitrogens. This is for sure an aromatic molecule, okay? And we can also even just do Huckel's count here too, right? These nitrogens appear to be sp3, so 1, 2, 3, those are 6 electrons, right? 3 pairs. An odd pairing, so this is an aromatic molecule. It's actually called inorganic benzene, for those of you that are interested in the name of that. So it's a real thing. I didn't just make that up, okay? Cool. So one little cool trick that I can teach you guys is that benzene, we know, is an aromatic molecule. So anytime you see benzene on a molecule, or you see something that looks like benzene but with atoms switched out, it is very likely going to be an aromatic molecule, like 99% of the time. For example, I can do this, right? And that's just benzene where I replace carbon with oxygen and nitrogen. It really doesn't matter that there's lone pairs on them. Again, an sp2 atom who has a lone pair is not going to contribute that lone pair into the pi system. They're perpendicular, right? We showed that last time with the with that turtle, right? The with the benzene turtle. So it doesn't matter. So this is clearly going to be aromatic. So much so you can actually even, one little joke molecule I like to draw is this hexaazine, right? This here is aromatic, right? Because it's just a benzene, just replace all the carbons with nitrogens, right? So as a benzene, I guess that's what you call that. Probably not, but cool. All right. So again, coming back to this molecule, again, the fact that there's a benzene kind of already tells you that this is aromatic. But you could also just do Huckel's count, right? So 2, 4, 6, 8, and then one of the lone pairs on this sp3 looking atom, not the other one. So 10, that's 10 electrons. So this would be an aromatic molecule. Okay. But actually, Huckel's rule was never made for polycyclics. It was made for monocyclics. So it's really interesting to me whenever I see questions where like you see everyone, not even just at Davis, it's everywhere online. You just see questions where they put 2 cyclic molecules together and they ask you if it's aromatic, and it's like, that's not how you're supposed to do it. Huckel's rule was only made for monocyclic molecules. But general rule of thumb, if there is a benzene feature in any molecule, it is very likely an aromatic molecule. A lot of people get really afraid when they see, like, for example, stuff like this, because they're like, oh, it's a benzene, but there's a non-conjugated ring, right? Because it's not conjugated because that carbon there. Doesn't matter. This is benzene, right? So this indene, this is called an indene. This is an aromatic molecule. Now, cool thing about indene is if you deprotonate it, right, you just make it, you just make that extra ring aromatic as well. Because now you have that cyclo. You just imagine the pi bond there instead of in the ring here, right? That's just a cyclopentadienyl anion. So this is another example of deprotonation leading to extra aromaticity. So this would be extra. It would be more acidic than you would normally think. Okay, cool. All right, so this is aromatic molecule. All right, aromaticity problems are never usually that crazy. Usually just some like non-aromatic and anti and then an aromatic. All right, cool. Moving on. Oh, I almost accidentally turned on my camera there. It's crazy. D, dienophile involved in the Diels-Alder adduct. So this is a bit of a crazy adduct, and when you look at it, it looks like I made a typo, which is always my goal, is to make things look like typos, because then you realize, oh wow, so they can really get this complicated, huh? So remember, in Diels-Alder, right, the simplest Diels-Alder is a diene with an alkene to make a cyclohexene. And the idea is that we put EDGs on the diene, which would go like, for example, here, or like here. And then we put EWGs on the dienophile, right? And so they would go here. So you guys can kind of see that the Diels-Alder at its finest can generate up to 3 stereocenters. And we can kind of trace back every carbon back. So for example, always the alkene is it's our savior, because the alkene signals to us where the 2 dienophile carbons are. It's always across. So across from the alkene is the dienophile carbons. And then these are our diene carbons right here. So if I wanted to, I could trace those back as such. Okay, just like that. And so I can tell exactly who went where, who came from who, right? So don't be afraid of any Diels-Alder adduct. Just use the alkene to guide you. Now, where things get tricky is when you use alkynes, right? Because alkynes can also react in Diels-Alder, something I always forget, to be honest. But what you get out is a cyclohexadiene. So if you had a diene, it's like, uh-oh, how do I use your rule? How do I, kind of trick this, man? You told us that we could just, use the alkene to guide us. And you still can. Just remember, the diene has to be electron deficient. Sorry, electron rich. The dienophile has to be electron deficient. So use EWGs and EDGs to help you here, right? This is how you sort of escalate the problem into a much more higher level problem, something that's more worthy for an exam. So for example, in this here, right, again, there are 2 alkenes, so boo-hoo. Clearly this was a diene with an alkene, an alkyne dienophile. But again, just look for electron richness, electron deficiency to find out your diene and your dienophile. So let's say I wanted to find the diene alkene, because that's usually the alkene is associated with the diene. Which pi bond here is a more electron rich, right? Which one has the donating group on it? Hopefully you guys are more comfortable with that now. It's the one with the lone pair conjugated to that pi bond. So this here is going to be our diene alkene. And obviously I drew it in a way where it's flipped over to trick you guys, because I'm tricky like that. And then again, across from the diene alkene is always the dienophile alkene. So there you go. That's we're going to cut right here. So we're just going to have a triple bond with a, looks like a ketone. And then we have all this here, where we have the methoxy here, this here, this here, this here, and this here. Okay. How do I know that the diene is going to have these 2 methyls pointing outwards instead of pointing inwards? Remember, pointing inwards is an NR reaction, right? There's too much steric hindrance for this to be cis. So in fact, it will be like this. So if I wanted the diene, I mean, I can figure out either one with confidence, right? Which one is which? I have absolutely no doubts as to what the product is. So I drew all these crazy products here to throw you guys off, but you didn't need that, because if you ignore them and just look at this guy here, easily figure out this is the guy we want to look at. Okay, cool. All right. And again, just to show you guys that this trick also works on this here, right? Again, imagine if, so normally you'll get the alkene over here if they're nice to you. And you can get something like this. And then it's like, okay, across from the alkene. So over here, these are our diene carbons. So you can get rid of that, which means we'll have this here. So this is our diene, and then this is our dienophile. Of course, this is way too easy. So why would they ever ask this question, right? Never, 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 never. So instead, what you're probably likely to get asked is where the diene is here, right? On the bridge, or supposedly on the bridge. And so now you've got to figure out, how do I cut this? Again, use your knowledge of EDGs and EWGs to help you out, right? If I have to choose between here and here for my possible dienophile carbons, I'm going to obviously choose these guys here, because those have EWGs. Okay, so I'll cut right there. And again, that just means that I'll form this. That's my diene. And then this is my dienophile. Okay. A lot of you guys are always afraid that you have to draw everything out planar. No, you don't. You just got to draw the right answer. So if you wanted to, I mean, you could get away with drawing this. Just draw it a little bit nicer than I do, right? That way your TA doesn't fight with you guys. But, you could always draw it like this. I actually no, never mind. You know, I realize now this would actually be kind of cringe to draw it like this because it's bent. So I would try to translate it over, right? Like there's a diene with a bridge, so there'll be, how about this? Let's just count the carbons. Let's make this the easiest possible. 1, 2, 3, 4, 5, 6, right? And then just kind of put everything relative. So there's a diene for sure, and then across from the diene of the two carbons is going to be the two methyls. Okay, so let's not do what I was going to do. I would have failed that question. Cool. All right, call it on there. Just to move on, save some time. All right, figured it out. Right. Cool. Moving on to predicted products. So we have aniline. Remember, free anilines or nitrogen lone pairs are the worst lone pairs on the planet. They do everything you don't want them to do. For example, if you try to do a Friedel-Crafts alkylation or an acylation, let's say you try to do an alkylation. Alkylation results in the quaternary ammonium. It overreacts. The nitrogen will continue to react over and over with those R groups. So alkylations is terrible. On acylations, right, it is a bit more controlled. You get one acylation, but you still get acylation on N first. It's a better nucleophile. Okay. If you wanted to do the Friedel-Crafts now, you could, and you could get the majority pair product, right, in synthesis. But generally speaking, if you ever see an aniline or a phenol, right, these two are the ones that are the weirdos, right? So if you have a phenol, remember that phenol and aniline, these lone pairs here are much more reactive than the ones in the benzene. So those electrons in the benzene are just a bit more stable. Okay. Don't forget, anilines are also very good bases. So anytime you try to do an H plus type reaction, so like an H2SO4 dehydration type reaction, we form the anilinium, which is actually a withdrawing group. So now it's the meta positions that tend to react. Okay. Cool. All right. B, actually let's see. So apparently on the key I made a mistake on this. I wouldn't be surprised. I kind of rushed through this. So let's see if I make that same mistake again. But again, if we want to do this the way, like the foolproof way, without using brain gymnastics, easiest way to do this is just to protonate both pi bonds and just see which one forms the better allyl cation. So if I protonate on the left side, right, I get these two allyl cations. So again, I start with the tertiary. I'm already really happy with that. But this here is primary. So I think I see the mistake that I made. I think I in my mind protonated the left one and thought, okay, tertiary cation, that's the winner. Because I didn't consider that. So that's probably where I messed up. So see if I can make the mistake, you guys can too. So even more proof that you should just draw both out. So you have the time on the exam to do it. Just do it. Yeah. This is also tertiary, but results in a secondary partner. So in fact, actually, we want to go with this one here. So the 1,4 addition that we want to go with is going to be the bottom one here. So this will determine our kinetics and thermodynamics. So this would be our kinetic product. This would be our thermodynamic product. And so we are at ADC. So we're going to want to do this product here. Cool. And then remember, this will be dash wedge. So this will be racemic. Okay. Cool. All right. So always just draw out the cation. This trick, this like kinetic thermodynamic trick will work 90% of the time. I don't know if you guys have friends from I don't know, for a couple years ago. It's really infamous. The rules around this for Nasiri's class are really convoluted, actually. In fact, actually, one day before the exam, Dr. Nasiri actually had released, she released a sheet that explained dienes really quickly in her own way, which completely contradicted everything that had been taught by me, the ATC, by tutors and all that. And it was like a very crazy hour of my day where I had to figure out what it was that that sheet was saying and kind of learn the rules all over again. So kind of a funny experience. So just use this trick where you draw all four, look for the best cation allylically, and use that to determine kinetic and thermal. You will get 90% of the questions right. Here's the thing. If you don't get the question right, like if let's say you accidentally on the exam actually get the one that's the exception that won't work with this trick, you will at least get partial. It's only ever one question. And again, 2-3 points is better than 0. So count your losses, right? That's what I always tell people. Cool. All right, you can imagine. Oh yeah, and then if I wanted the kinetic product, that would just be this here. Okay. Don't forget, if this was DBR, don't be afraid of it. You just have to draw the deuterium, right? You have to draw out the D. So that's why I drew out the H. just to get in the habit of doing that. And remember, if it's DBr, you just got to draw it out. Okay, cool. All right, moving on. We have this system here. Looks like an alo chloride, and we have methanol and heat. So you can imagine the chloride will leave because methanol is not a good enough nucleophile unless it, this ionizes. And then again, we have an alo cation. So this cation potentially can resonate. Hopefully, once I draw the resonance form, you guys can see what the point of the question was. So I'll resonate that right pi bond over. But we get this alo cation here. We kind of have a kinetic cation and we have a thermodynamic cation. We're in heat. So you can imagine over time, eventually, all the product will convert over into this over here. Oops, sorry, not that. This. Apologize. Into this over here. Okay. So with these, allylic type systems, right, always look out for those resonance. I think for the most part, if you go with the thermodynamic product, you'll be fine. Again, it really does depend on whether it's, heated or not, but usually these questions are. So right. These are not dying problems, by the way. This is not a dying problem, because a dying problem results in an allyl cation. This is actually a diallyl or a bis-allyl cation, right? It's not exactly the same. And if anything, this results from a triene, right? Right, a triene. If I did a reaction with a triene, this is like kind of the equivalent of that. Oops, sorry. Oh, oops. That's why it was weird. It shouldn't be too hard to see which cation here, like out of these three, which one's thermodynamic and which one's kinetic. Kinetically, well, actually, two of these are, yeah, so two of these cations are actually really stable, right? They're both secondary. So I would say if I had to put my money on the kinetic here, I mean, kinetically, this one forms literally initially, and it is more stable than this one here, right? Simply because well, I guess, how would you determine stability here, right? I don't want to use this term. I was trying to avoid using this term, but if you look here, this is like linearly conjugated, as in the electrons can kind of flow in one direction. This here is not linearly conjugated. These have opposing directions of flow. We call this cross conjugation. It just means cross conjugation just means the electrons can't flow nicely, right? They have to kind of collide into each other. And cross conjugation essentially slightly destabilizes. You'll see this at 118C. You'll see this at 118C where you have two conflicting sources of electrons, right? So like, for example, like an oxygen and a nitrogen, right? These both can't resonate at the same time, or they can't flow electrons nicely at the same time. So they kind of compete for that cation. The competition results in a slight destabilization, right? Because you don't have the maximum amount of electrons being able to flow in. Cool. All right. So this here is linear conjugated because the electrons can flow very nicely, right? They can just all flow together to the end. And I'm sure there's some MO theory for that too. So this would be my contender for kinetic. And then this here would be my contender for thermodynamic, which should be fairly simple, right? Remember, thermodynamic just thinks about the alkene, the diene stability. So these are conjugated. Both of these do have conjugated dienes, but this diene is much more stable, right? So they're both secondary here. This one's primary. Okay, cool. All right, call it on there. Got ourselves a diene and an alkene, or dienophile. So we have a diene. We have a Diels-Alder reaction here. If I just kind of flip this guy on its side, just like that, I can kind of see what the diene looks like. Or it's got a better picture of it, right? Actually, let's use that trick that I taught you guys. So let's say that I have this here. Remember, just use the relative like positioning. So for example, the fact that, okay, this right here is just a terminal alkene, so I can just pretend that's this one here. But the fact that this nitrogen and this alkene are trans to each other must mean that if this guy is here, if this guy is here, then the nitrogen must be here. So this is an outside nitrogen. So I wasn't very creative with these Diels-Alders, I guess, kept putting them on the outside. And there's just a methyl right next door like that. Okay. So this is like a 1 sub, 2 sub where they cooperate, that foolproof Diels-Alder. So when I draw my product here, right, again, the positive is here, the minus, oh, actually, no, this is not a foolproof, actually. This is a competition. All right, this guy sends here, And then this guy sends here. But remember, resonance donates are stronger. So we'll go with the nitrogen as a director here, right? We'll get the attack just like that. So make our cyclohexene. Nitrogen's going to be here on the outside. I'll give it a wedge just because I want to. And then I'll have my amide here, right? And remember, the pi group, this is a pi group, so we'll give this a wedge. This will also be a wedge because it was a cis alkene, and that must be the same as the outside group, just like that. So we'll put here racemic. Okay. If that nitrogen was on the inside, so let's say, for example, like as a ring, so let's say pyrrole. Pyrrole is very good at doing these reactions, despite being aromatic. Right. Then now if I give this nitrogen a wedge, right, then the group here's got to be a dash, right? Because now it's on the inside. It's a pretty bad drawing. I apologize. There you go. It's a little bit better. Cool. All right. Moving on to E. So remember, when it comes to allele systems, radical cation and anion, the radical and the cation are similar in that you want to form the most stable radical anion that's more substituted. So generally, if I were doing a radical reaction here, I would only consider really these two positions for radical. Or, I mean, cation will require a leaving group, so it's like whatever. But for like a radical, I would look here and here. Anions prefer to be less sub. So actually, out of all these positions, it's really this position here that I care about. Okay, so anions like being less sub. So we'll go ahead and form that there. And now we'll just go attack there. So essentially, remember, whenever we add Grignard fragments, we're adding a carbon with an alcohol, and then whatever the carbon chain is. Okay, so there we have that. Now, cool little thing here. Let's say that is a dehydration, right? Which side would my alkene form on? Right, technically, on this alcohol, this carbon and this carbon are secondary. So would it, almost feel like it wouldn't matter. But let's draw the result of that left dehydration. And what do we get? A diene. So start to get comfortable with forming these dienes or how to form these dienes, because as we'll see in the synthesis, again, dienes have a lot of utility. You can do a lot of things with them. You can make things with them. So being very comfortable on how to make these in different ways, rather just one way, will help expand your ability to see how to do, like, for example, Diels-Alders in synthesis. Okay. Cool. All right, F. So F, we have two meta directors. We have a Friedel-Crafts electrophile. 2 seconds. What's the answer? The answer is NR. Remember, Friedel-Crafts will never happen on meta directing ring. Okay. Friedel-Crafts is the one that has like the most exceptions too, really. So we'll see in the next exam. There's another exception to know for Friedel-Crafts. Cool. All right. G, we have an ester, where we have a carbonyl and we have an oxygen lone pair. A lot of people, when they see esters, get really scared and they think they have to guess whether it's meta or orthopair directing. Remember, the effect is always going to be from the atom that's connected to the ring. So yes, there is a withdrawing carbonyl here, but it's the lone pair oxygen that is conjugated. So this is going to have an orthopair effect. So first thing we'll go para, right? That's always the first electrophile goes para in an orthopair situation. Second electrophile go ortho. Now imagine if I did a hydrolysis after this. So it's H3O plus and heat, right? It's almost as if the sulfur were not even there. So remember, in synthesis, right, para is always going to be the first addition, major addition, or substitution. That's always going to happen first. So if you end up with a product that is ortho substituted only, don't just throw on the activating group and then just do ortho para direction once and add the thing ortho. It's not the point, right? The point is to do the sulfonation first and then the whatever is ortho. Okay, cool. All right. H is alkyl chloride, AlCl3. So we can assume here. Remember, Friedel-Crafts alkylations are essentially SN1 type reactions. So we can form the cation here, and hopefully you guys can see what's going on. The benzene, the cation are right there. So go ahead and attack just like that. So intermolecular, right? This is really where the intermoleculars come in. It's in these Friedel-Crafts alkylation reactions. Okay, cool. Now remember, these are just cationic reactions. So you can imagine that in fact, you could have even done this reaction with an alkene. That would have worked too. Alkene and like HF. something, non-nucleophilic, that would have done it. That would have also formed the same cation and the same cyclization. So just look out for that. Don't be surprised if that's a possible problem on the exam. I don't know, what's the craziest thing you could do here? Probably like a ring. Right. And then in this case, this would form here, attack like that. So you can get pretty crazy. Oh no, sorry, 5. So this would be the benzene. And then on this position would be a ring here, like that. Cool. All right. So, oh, nope, that's wrong. The ring is on like that. Yeah. There we go. Yeah. So that looks, we call this a spiro compound. When a ring is fused onto one carbon, it'll look like that. So don't be afraid of seeing craziness like that. Cool. All right. So ring the products, not too bad, right? Not too shabby. Hopefully that made sense. Cool. All right. Mechanism, sulfonation. Remember, if you have orthopair director, usually, I mean, whenever the electrophile is bulky, so in this case, this is a bulky electrophile, or the substituent is bulky, so it's a branchy, bulky substituent, right? Para is going to be the major product. This is an H2SO4, so it's a dehydration, so that shouldn't be too bad, right? We can even just sketch this really quickly. This whole reaction is reversible, so all arrows should be double-headed. So this will form water, right? This oxygen will help kick it off, and then we form our electrophile, our super electrophile. And then from here, right, just benzene attacks and then does its resonances and then, does the elimination. Okay, cool. So I'm not gonna get into much more than that, but that's that there. All right, synthesis. So these are a little more crazier. Not the easiest, but it's still doable. The first one is a favorite of mine, just because it shows you that you can start with gasoline and you can inspire some complex, very complex. You can do some very complex or add some complexity to this. Right, gets pretty crazy really quickly. Okay, cool. So I mean, if we look at this, we see the cyclohexene, right? Clearly, this is a Diels-Alder. Again, there's only one alkene here, so thank God. That means that we only have to focus on that one alkene and say across is that dienophile. So I'm gonna go ahead and cut these off here, and get rid of that dienophile, and say, right. So this is our dienophile here, right, and then our diene will just be this here. And so if you kind of think about it, right, we have, we have these 5 carbons here, which mirrors this 5 carbons. So clearly we're forming the diene here. Okay. And so as you guys kind of saw in that last midterms exam, right, where we started from a cyclohexane and turned into benzene, it's the same exact sequence of adding alkenes and doing NBS and all that whatnot. So you can do NBS HV here. A lot of you guys probably think, oh, isn't NBS the allylic reagent? No, NBS is just a brominating reagent generally. It's just preferred in the allylic radical reaction, so that you don't get the pi bond addition instead. But we can do NBS. A lot of you guys last time also were like, oh, how do I know whether it goes here or here? It doesn't matter. If you're really worried, you can draw both, right? In either case, we're just gonna eliminate and form an alkene. So for these ones, so either case, you're gonna want to form this alkene here, right? So just small base will do it. Any small base will do this. And then we'll go ahead and do our allylic bromination. The nice thing about this one is that the product is symmetric regardless of which one you form. Right, these are the same. So lucky us, right? And then we'll just do a bulky base elimination now. You can still use a small base actually, because this proton is still going to be preferred in the elimination. Actually, there's only one proton, so I mean, you're not gonna get a substitution. So whether you use bulky or small, it's really up to you, but either one will work, right? And there you go. So Diels-Alder, pretty easy, right? One of the ways to kind of increase complexity or make this a little harder to think about is you do a subsequent reaction on the alkene. That's kind of throws people off sometimes. Like for example, let's say we add Br across this. And then people are like, oh my God, this is wild. How are we doing this? Remember that alkenes inspire vicinal functionality. So you can always trace back to the alkene very easily, just that vicinality tells you that. I mean, and anything is really acceptable here. Imagine if there's like an epoxide right here just hanging out. That'd be a really funny thing to add here, like an epoxide. And you're like, oh my God, like what in the world? This is not fair. Yeah, it's pretty fair. You just have to remember that from the last midterm. Oops, forgot that there. Okay, so that's a way to increase complexity. By far the craziest, I mean, if you think about the craziest reaction you could possibly do to increase complexity, probably be this one here. So you have to think about, maybe some of you might have to think about this one for a second, what it is that I've done here. Maybe if I draw it like that, you'll see what it is that I've done. I've essentially done an osmolysis, which kind of destroys the Diels-Alder ring altogether. Right? Because I mean, you could draw it like this. This would probably be the hardest way to see this, but I would say if you ever see something like this again, I would just quickly count from aldehyde to aldehyde, right? That's the easiest way to introduce two aldehydes or two carbonyls, right? 1, 2, 3, 4, 5, 6. That would be my giveaway that this is a Diels-Alder, is that there's 6 carbons away from each other, and you have that dialdehyde. So that 1,6-dialdehyde, right? That would be a wild one, in my opinion. Cool. All right. So we'll just call it there on that, just for sake of time. I think we're pretty good on pacing right now. Probably approaching about, I think we're at the 45-minute mark right now. You guys let me know if I'm correct or not. Cool. All right. Now this one was a tricky one because when you look at it, you can clearly see that we're adding in what appears to be like an alkyl chain, so maybe some kind of Friedel-Crafts electrophile, but we're doing it to an NO2 ring, and this was done very purposefully. Obviously, this on purpose. The reason why we start with the NO2 is to kind of force you down a certain route. Okay, so clearly this NO2 is just this NH2 here, right? It's just a reduction of that. So we can go backwards one step and say, okay, they just did a reduction. And there's a lot of things you can do. I remember this one being the particular one that's specific to NO2. Okay, cool. So you get to here. And so now you got to figure out how to add in this alkyl chain, this alcohol chain really, onto this ring. But we start with NO2. And remember, doing Friedel-Crafts here is kind of illegal because Friedel-Crafts you can't do on an NO2 ring. Now, maybe you think, oh, let me just reduce to NH2 and do it. Well, if I did reduce to NH2, and let's say even protect, right? That's ortho-para directing, so I can't even do that. So this is just not going to work. So what is it that I can possibly do that'll help me out here? Well, don't forget that Friedel-Crafts isn't the only way to make CC bonds. It's just the easiest way to do it on a benzene ring. The most traditional way of making CC bonds is the Grignard reaction. So if I consider breaking this bond here, right, and I draw out my 2 pieces, right, the alcohol fragment will be my carbonyl or my epoxide, right? The other fragment will be my Grignard. But you can do this here. Right. The trick that I use is that, if you put a star or some kind of indicator on the carbon that's next to the that you cut off, from the ring. So I cut off directly here. So this carbon here. If that marker is next to the alcohol, then it's a carbonyl. If it's a 1 over, then it's an epoxide. So, for example, so in this case, right, obviously, then this becomes this here. This is the ketone that we use, and this is the Grignard that we're doing. An example of an epoxide would be like, let's say instead it was something like this, where the marker were like here, right? That's the indicator that this comes from an epoxide. And it's really easy to draw. You just kind of slam the oxygen down on that position, and then you get this here. Although, I mean, obviously now this doesn't make sense, right? Because it's like, oh, in what universe does it go? I mean, again, this is just this is not well thought out, actually. I'll do this instead. How about this? Right. And now it makes much more sense why it opened up on that side. Okay. So yeah. So things to think about, right? If they were an epoxide, right, it could possibly have opened up. Cool. Anyways, Grignards come from bromides, and we know how to add a bromide, especially when it's meta to an NO2. That's just Br2, FeBr3. Mg ether, and then we'll just add this in here. Cool. So very non-traditional. This one's a bit trickier because it's kind of breaks some rules, and a lot of time people always kind of hyper focus in on things that we talked about You know, like, you know, students are very hyper focused on just the reactions of that chapter. Don't forget other classical reactions too. The CC bond formation, especially, very, very classic. Okay, cool. So is there any way that we could have riffed on this other than the epoxide? No, not really. I guess we could have done an alkene reaction here, like a Br2 or something. If I did Br2, right, that would form the bromonium here. Any ideas? I have a very good one. We could do this here. So it's sort of like an epoxide walking, right? Because we, or not epoxide, but it's epoxide formation, right? We can form an epoxide with the bromine on the end there. Unfortunately, we can't do anything cool where this NH2 kind of closes on that would not be a very good ring. So that'd be cool to think about though, if you could do that, but probably not very likely. Okay, cool. What else? I'm thinking, what else could I've done that's anything quirky or, man, I had an idea in my mind and I'm just like blanking. What is it that I had in mind? I don't remember. If I remember, I'll come back. But there was something that I drew. I drew something here, and then I thought, oh, I want to mention this. And now I can't even remember what it was. So, whatever. If I remember, I'll bring it up again. Cool. All right. NMR. I mean, clearly going to be some kind of benzene, right? So maybe we can do this real quick. 11 times 2, 22, plus 2, 24, minus 14, 10, divided by 2 is 5. So 4 of those will go in the benzene, right? We can even check here real quick, right? We see the band. That's what I mean by the band or the barcode. We see a line at 200. Remember, 160 to 180, that's when you have like an ester, right? 200, that's when you have a ketone or an aldehyde. Check the NMR, right? If there's something at like 9 or 10, like a 1H at 9 or 10, that's aldehyde. In that case, this stops at 8, so this is clearly a ketone. So I'll even just go ahead and, or I guess I'll draw in a ketone fragment, right? So I know that there's some kind of ketone in here. Okay. That must mean that the other oxygen in this formula is like an ether, because there's no alcohol in this either. So there'd be some kind of ether. So actually, probably if I just wanted to, I could probably just throw these on and get like a good amount of partial credit. But let's just get one more part right, right? One other part I can get right is the fact that we have kind of like a triplet, doublet, and then a singlet here. That singlet is the key to this reaction because that singlet tells us that this is meta substituted. Okay. So meta substitution, I'm almost even going to just do this and this, right? And then, okay, I have 2H quartet, 2H quartet. So, oh, quartets, triplets, right? That's what's going to be this here. Yeah, there you go. So not even in less than a minute, just kind of guessing where we can kind of go. Cool. All right. Okay. So with that, that's midterm 2B. I think we're making pretty good time. Just gotta kind of speed, because I think it's been an hour now. So we're just gonna kind of speed run through this one here, just to get it done as fast as possible. Cool. All right. So which of the terms best describes a chlorine substituent effect on benzene? Remember, chlorine has a lone pair, so it is going to be orthopair director. But halogens are also deactivating. So remember, those two terms don't always go hand in hand. So this is going to be orthopair director. Other things I would go here is oxygen with a lone pair or nitrogen with a lone pair, right? Ortho meta does not exist, but meta does. So if this were like an NO2, NR3 plus, right? CF3, right? Stuff like that. Okay. Nucleophile makes no sense for substituent effects, right? That's the benzene. The benzene itself is a nucleophile, right? But it is not the substituent effect, right? Benzene will always just be a nucleophile. And activator, right, would have worked if this were like an oxygen or a nitrogen, but chlorine is a deactivator, right? Cool. All right. Which alkene reacts the fastest in Diels-Alder? So these are dienophiles. Remember, electron deficient. So we're looking for EWGs, right? So clearly not the O that's conjugated with its lone pair. Bromine, is an orthopara, so it's easier to think about it as the weakest EDG. So clearly this guy is not going to be either. And carbons are EDG. So that leaves us with the NO2s that were very suggestively, it's very suggestive that that's going to be the one. Cool. All right. Which electrophile cannot react with benzene? So this is just if you know your 5 reactions, right? Remember, There are 2 H2SO4 reactions, and then there's technically 3 benzene type Lewis acid type reactions. So if it's not one of those, it's definitely not going to work. Bromide with FeBr3 forms the FeBr4, right? It's electrophile. This will work. HF, remember, this will form a carbocation, which is carbocations are electrophiles, right? Despite the fact that they don't react with nitrobenzenes, so this would suck in that case. This forms the this electrophile here. It's this here. This is MCPPA. MCPPA does not work on benzene, so the answer is this. Now, what's a way that they could ask this question where they show 4 things that do work usually on benzene is if they add nitrobenzene, or if they say nitrobenzene and ask the same question, but let's say with these 3, right? Remember, the only exception, the only reaction that does not work is the fatal crafts on metadirectors. So nitrobenzene, which is metadirected, fatal crafts, carbocations won't work. Okay, acyliums won't work either, right? Acyliums will not work either. Cool. All right. Be very comfortable with this, right? Knowing how to at least bullshit out orbitals, right? A diene, which has 2 pi bonds, will have 4 molecular p orbitals, which I'm drawing very quickly. Remember, ground state, very, very easy. You just draw in all these in phase. Then you do your first symmetric node, just like that. Then you do your 2 symmetric nodes, which is just like that. Okay, very good way to check that you are doing this correctly is to look at the ends of the molecular orbitals to see if they're in phase or out of phase, right? It should switch. So these are in phase, these are out of phase, these are in phase, so these should be out of phase. Okay, remember the highest one always has the maximum number of nodes, so it is quite, it's on there with the easiest, or it's up there with being one of the easiest ones. Okay, cool. So remember, diene has 2 pi bonds, so 4 electrons, so we can put those in, right? So at standard, so just standard temperature, standard heat, this is the HOMO, right? The highest occupied molecular orbital, and this is the LUMO, right? The lowest unoccupied molecular orbital. You can actually call this here the LOMO. This actually was asked once, so it was kind of funny. The LOMO, lowest occupied. Lowest occupied is always going to be the ground state, so there's a term there. Now, let's say that we added in a little stipulation here. We added in a little caveat and said, correct representation of diene a HOMO with exposure to light. Remember, light makes that electron jump up, right? Absorbs that wavelength, jumps up. So now the HOMO is going to be what used to be the LUMO. Okay, so just be aware of that. Okay, alkenes are also very easy to draw these for, right? Because alkenes just have 2. Wow, that's so easy, right? That's not very hard to do at all. There's just 2 of them. Probably the hardest is the is the triene. I don't even want to draw all of them. I'll just draw the ones that are relevant, I guess, for the triene. Here. For any of you that are like amazed that I have these like memorized, it's not really memorization. It's again just understanding how these nodes work. If you understand how they work, you can always do these at any time. Okay, so I'm only going to draw it for these because these are the only ones that it would matter for. Because in a triene, there's only 6 electrons, so it would only ever go up, right? 3. Like it would fill up 3, so this would be our HOMO, and our LUMO would be up here, right? I guess if there's like an HV excitation, right, it would differ. Okay. Yeah, actually, I would almost even recommend you guys try to do this on your own first, and then afterwards, right, see if you get this right. Okay, but always remember the ground state is always going to be all in phase, and ask yourself, how do I make a symmetric node in the next state up, right? Because you add 1. It's very simple, right? So it's down the middle. So it's just like the 4, where you would do this, right? I imagine some of you probably would get stuck here, in this third one, because you're thinking about how to add 2 of them, but actually it's not very hard, right? Just add 2 like that. Right, makes it symmetric. It's kind of like how in this one here it was like on the ends, right? Okay. Maybe three might be a difficult one. But actually if you kind of mirror this one here, it's just kind of the same thing, right? Just kind of look for ways to kind of make sure they're symmetric. So that's symmetric, and then these two are symmetric in the middle. Again, we can check these are in phase, these are out of phase, these are in phase, these are out of phase. So if I wanted to make the next one up, oh, next one up is actually pretty difficult. I actually don't know if I remember how to do this one. Let me see. So let's want to do the next one up. How could I add 4? How could I do 4? I guess I could do. Oh, I guess you could do this. Yeah. So almost everything out of phase, but the 2 in the middle. Yeah, that would work. Right. And then these are in phase. Yeah, that works. Okay, cool. So homo lumo, this is the triene. If I did HV, right, then this would be the homo, this would be the lumo. And then, yeah, cool. Trying to think, is there any other one that might be worth just doing just to do it? Oh, I guess yeah, there actually is one that's worth doing. So I'm gonna just clear this, but there's the 5. The 5 is difficult. I think the 6, again, as long as you know, it's very easy to see the symmetry in 6. It's just like 4. 5 though is a bit difficult. Because it's like 3 where it's like it has that like asymmetric number, right? So when we get to here again, how do we make that first symmetric node, right? It's like the 3 where you kind of go down the middle of one. So these are in phase with either out. And then again, when we get to here, right, how can we make 2 symmetric nodes? Now this is a tricky one. This is a tricky one. I think maybe the thing that you guys might think is doing down like this, right? So phase, in phase, and then phase. That could work, right? But in fact, it's not going to be this, right? Even though it feels like that would work, it's not. This one is really tricky. I don't think they'll ask you this one unless she has shown it to you. This actually goes down the middle of these guys. Whoa, trippy, right? Like, how would you have guessed that? I definitely would not have. So this is for the cyclopentad, or sorry, not the cyclopentad. This is just for like an alkene like this, and then if there's like a radical, a cation, or an anion. So obviously there's going to be 4 electrons at least, and then it'll be a matter of this orbital here whether it's full or not. So it'll depend. If it's a cation, this is the HOMO, right? If it's the anion, then this is the HOMO, right? Because like an anion would be like a 6 pair of electrons. Okay, so let's just kind of think about what the. Yeah, I think I'll just show you guys. I remember it being weird for this one too. If I remember correctly, I think it's oh wait, no, I think it's this. Wait. Sorry, let me try these in again. How do they look again? Oh, right. It's this, and then get rid of that. And then this. Yeah, this one's a hard one. So be careful here. This is not an like there used to be one here. It's going down the middle of this one. So yeah, it's a hard one. So spear limo. Cool. All right. I've talked too much about the orbitals now. I think you guys' brains are rotting just like mine. So we won't entertain this any longer. Just move on with this. But I just wanted to draw them just so if you wanted to have them down to practice, you'd have them. Yeah. Cool. All right. Sorry, give me 1 second. Cool. All right. Oh, I didn't even. Okay. Haha, funny. Whatever. Cool. All right, moving on to predict the products. So these were a little bit more difficult, but nothing too crazy. First one, we have an aniline bromine CF3. We're doing an acid type reaction. So imagine a lot of you guys instantly probably did something like this. You said, oh, the strongest activator is the NH2, so either here, here, or here. So the NO2 goes here. If you did that, you're practicing good logic. You just forgot one thing. We're in acid. So in fact, actually, this is an anilinium. And aniliniums are withdrawing groups. So we have 2 withdrawing groups here, and we have this, well, 3 of them. Only one of them actually has a lone pair. The bromine is actually what directs. So bromine will either direct here, here, or here. It's always going to direct para here. Okay. So let this be a lesson to all of you. Don't forget the aniline pertinates. Okay. So it's a bit of a pesky little thing, right? Kind of have to deal with that. Cool. All right. Now, if this were protected, then yes. So let's say this were NH like that, then yes, this would go right there. But the fact that it was not is the reason why we got it right here. Cool. All right. Moving on to B, right? We have this allyl bromide, and we have this guy here. So a lot of you guys are probably going to do something like this. Probably will draw this cation and then think, oh, it's heated, so it's just like the last one. So it might be something like this, where it forms this conjugated diene that's a bit more linear. Well, actually, sorry, no, these are the same. My bad. These are the same. I was thinking of the 6 membered in my brain. My bad. But yeah, so it formed the 2 that are the same. So it's like, okay, go ahead and do that. I'm going to draw this again for you, and I want you guys to look at this for a second. Think about it. Tell me why this would not work. We have conjugated system, that's a ring, and we have 4 pi electrons. This is anti-aromatic. This is going to be NR. This is never going to work. Okay. Or if it does, it's incredibly slow. So slow that we consider NR. Okay. So don't forget, if you ever see the conjugated rings, you got to think about aromaticity. That's the whole point. The whole point of these conjugated rings. Okay. Another example of this that is a little, it's harder to think about, but it is still possible, is this here. Let's say that this ionized as well, right? This is an aromatic cation. It's an aromatic ring. This is also going to be NR. Okay. So, whoa, what gives? Why are they both NR? Okay. Because of that little thing that I mentioned, right? Remember, aromatics, when it comes to aromatics, they form the fastest. So this forms the fastest. Okay. So that forms the fastest, but it reacts the slowest because it's aromatic. If we react with it, we get rid of that aromaticity, right? Which is like, that's bad. We don't want to lose that. Okay. So it forms the fastest, but it reacts the slowest, right? They're up there with the reactivity of a, if anything, anti-aromatic cations react the fastest. So if you were given an anti-aromatic cation, right, this forms the slowest, but it reacts the fastest, right? But that doesn't matter because who cares how fast it reacts? The long part, the rate determining, is the forming step. So this forms the slowest as well. So this forms the slowest. So it's a, I hate to say it, but this is a very much a like, it's a very vocab-y kind of section, right? For multiple choice. Like, if you're asked which cation forms the fastest, you want to go with the aromatic. The fastest reacting cation, though, will be the non-aromatic, right? Because aromatic cations will not react at all. Anti-aromatic cations won't even form, right? They form at obviously the slowest. Non-aromatic alkenes will be the ones that form relatively, in the middle in terms of speed, but they react faster than aromatic cations and faster than aromatic anti-aromatic cations as well. Or sorry, they form faster than anti-aromatic cations. So cool. All right, that's a tricky one. Yeah, it's a tricky one. Cool. All right. So I guess to kind of to summarize, if this were the question as well, this would also be NR. Okay. Cool. C, we have 2 bromides, one that's next to the pi bond, one that isn't. So you can imagine this is an allyl versus non-allyl question. If I have only 1 mole of sulfur, should not surprise any of you that this is the reaction that we get, right? You could put racemic if you want to. There's no information on this like the, I guess there is. I guess, actually, let's make this question 10 times better. Let's do that. So before it would have been racemic because technically this was racemic at the beginning, but let's make it stereospecific, right? Now it matters who you substitute and how you substitute, because this is a sulfide, so it goes by SN2. So the sulfide will substitute via SN2 inversion. This bromide will stay the same though. So that's a very good way of asking this question. Cool. Now here's the cool little thing. Just actually, no, never mind. No cool things today. We need to stay on time. Cool. All right. We have a sulfur or sulfuric acid. We have a hydrolysis sequence. Hydrolysis gets rid of the sulfur. Just remember that we are doing this in D2O. So that means that instead of just having hydrogen here, we have deuterium. Okay. So just be careful with that. Deuteriums, you do have to label, the whole point of them, so that we can see them. Okay. But normally if it's just H2O, H2SO4, it's a hydrogen. Cool. All right. E, we have symmetric dying, so it doesn't matter who we react with. The bromide might throw you off, but just remember, the bromide is the electrophile, the water is the nucleophile. So this is the 1 part, and this would be the 2,4 part, right? Depending on what it is. So I mean, it doesn't matter who you react with; both are. It's a symmetric dying. So the bromine, let's say we react with the top one, right? We'll get this here. And we'll get this here. Oops, sorry. This here. Okay. And then water can capture on either one of these cations. If I remember correctly for this class, the bromide additions are you're always going to draw both, from what I remember. I remember that being a thing, even though that's not true. There is still a thermokinetic, but I think just for the sake of simplicity for you guys, it's just, you just draw both. So yeah, so we would draw both of those. Cool. All right. Now let's get rid of the asymmetry for a second. Because again, this is the much more fun problem to do. Again, you want to draw both allocations, right? So you can draw this, although you can kind of see now, like if I do the top one, this is why that trick of most nucleophilic pi bonds not always going to work, right? Because it doesn't make sense here, right? This cation is not the most stable cation. It completely avoids the tertiary position. So it's definitely going to be that this bottom set here, right? And this is if we protonate on the bottom side. So sorry, let me throw on the bromines. I forgot to throw on the bromines. Right. So we're going to brominate or add the electrophile on the bottom side there. And then again, water will just add to the cations here. So yeah, we'll get these two. Just fact check me on that. I don't remember, to be honest. I just remember there being some kind of deal where these ones were always like both. Cool. Now, in terms of stereochemistry, stereochemistry is a little tricky on these, because technically they're, I mean, you know, I haven't really drawn a bromonium ring, but there could have been one, right? I would say for the 1-2, it's okay to go with the anti-stereochemistry, like that. So if it's the 1-2, you can go with anti-stereochemistry and then say racemic. But this one, I mean, you really don't know. You don't know whether it's this or whether it's the other one. So let's just hope that whatever questions asked kind of doesn't, you know, go too crazy on this, because it could be the sin anti, it could be the sin, or it could be the anti, right? You don't know. So it'd be like a lot of products in this one. Cool. All right. Moving on. F, we have a triene in heat, right? Remember, trienes and squares, those are our electrocyclics. Or trienes and, or actually, yeah, I guess I'll draw it this way, because you guys should understand it this way. It's better to understand it this way, right? Thermodynamically, squares like to be open as butadienes, and thermodynamically, trienes like to be closed as cyclohexadienes. Okay. So that being said, right, if we wanted to reverse these selectivities, right, we would use HV. Right, HV is kind of like the you know, anti-thermodynamic, I guess. So to close square, just close into squares, we use HVs. To open into trines, we use HV. Okay. So, I mean, this is just a thermodynamic preference, right? Just to be this here. And no stereochemistry, so don't worry about it, right? Lucky for you guys. Now, let's say that I have a butadiene and I just use heat, right? Oh, sorry, heat, right? Obviously, this is NR. I don't know if I would say if it's NR to just heat a trine to get this. I think it works still. But generally speaking, it's very difficult to do. So let's hope that that question is avoided to do a heating of the cyclohexadiene. Cool. All right. Maybe you guys are getting some ideas. You see another diene we can form here. Maybe there's a good question that could come out of that, right? All right. We have this guy here, this diene, and we have a dienophile. So Diels-Alder. So I can go instantly draw my cyclohexene, right? I'll put my dienophile here. Right, put wedge. I have a ring diene, so I'm gonna have a bridge here of two carbons, or sorry, two atoms, nitrogen and the carbon, right? Actually, I'm gonna get rid of these wedges. I like making the bridge a wedge. It's just easier, in my opinion, to make the bridge a wedge. So I'll do that, and then I'll make this a dash, right? Remember, the bridge is always an inside group, so the dienophile will be opposite to that. And then we have a methyl here. Okay. Now, one thing that's a little, I mean, it wouldn't have mattered here because like both of these, but let's say that this carbonyl were not there. We would still want to obey the 1, 2, 1, 4 rules, or the closest possible or farthest away possible, and that this is a 1 sub, so the ketone wants to be right next door, and that's what we do have. Okay. But we did have a carbonyl there, so it didn't matter. Cool. And we'll just call this racemic because you don't know whether it adds from the top or the bottom. Cool. All right. We have anisole. We have a methoxybenzene, and we have, looks like a vinyl chloride, FeCl3. So this to us looks like it might be Friedel-Crafts. Don't forget the cardinal rule of Friedel-Crafts. Friedel-Crafts is for alkyl and acyl chlorides. So what does that mean? What does that mean? What that means is that you can use chlorides that are attached to sp3 carbons, right? You can use chlorides that are attached to carbonyl carbons. Okay, but you cannot use any chloride that's attached to anything else usually. So vinyl attached to a alkene, loud incorrect buzzer. Alkyl chlorides, can't use that either. So classic NR question. And you can prove this very easily by forming the cation, right? sp3 can form the cation the easiest. So let's just put on something that is feasible like this. The reason why we can do it on the acylium or in the acylium is because of that resonance stabilization. So that's the only reason why that can form. And then if I draw these here, this is the worst possible cation. Don't ever draw it. And if I form this here, this cation can't even resonate. Okay. So don't forget aryl cations, those guys can resonate. So this would be viable. So this would be okay, but this is bad and this is bad. Cool. All right. Calling it there. Mechanism is a little tricky, or might be a little scary. Don't worry. I'll just go over the electrophile part. Don't be afraid if you see an anhydride. Remember, anhydrides are just like acyl chloride. So in the acyl chloride mechanism, you add the metal here, and then it travels to the other group, and then this falls off, right, to form the cation. All this is just to facilitate formation of the acylium. So don't be afraid of it. It's pretty much the same. We'll just go through it. So this will attack AlCl3. That will get this first. Remember, carbonyl oxygens, those just bond really well with metals. Okay. And then this will eventually transform into the salt, where we're added onto the that carbon that's, or the oxygen, or that group next to the carbonyl, or in this case oxygen. Once this happens, right, that oxygen is going to leave, and we form the acylium cation. Okay. Now, just to be careful here, just so you guys don't lose any points, I would always just draw the resonance form where the electrons swoop down and form the acylium. Remember, the acylium is linear. It's a triple bond, so please do not draw it with a kink in it. Don't draw it standing up. That's just asking your TA to laugh at you, right? And possibly take away points. But we'll have this, and then benzene, right? We'll do its attack on here. I'm not going to show that because, again, it's just attack, resonate, eliminate, and then we get out. I mean, I'll draw what we get out, but we'll get out this here. 1, 2, 3, 4. So 1, 2, 3, 4. Okay. Just do not forget the most important thing, which is that this will go ahead and complexate again. So that's why we need a full equivalent. Acylations need a full equivalent. They're not catalytic like alkylations. Okay. Hydrolysis is what breaks this up. Right. Hydrolysis is what breaks that up. So cool. So H3O plus, right, will kind of protonate everything, get rid of things. Just like that. Okay, cool. All right. So there you have it. That's the mechanism for the most part, or in parts, at least in my opinion. Cool. All right. 5, synthesis. Not too bad. Let's start with the bottom one first. This is easier, right? We have a phenol going to a ortho-substituted benzene. Remember, ortho substitution, you might see the phenol and think, okay, I just need to add something here. I just do like 2 steps and this is it. But remember, whenever you do ortho-para direction, the major product is always para. So that's kind of the trick in this one. But again, let's just kind of look at this and kind of see what things are being added and how we can work backwards. One of the easiest things you can work off are these acetate groups or these like carbonyl groups, because those are just protecting groups, right? So we can, well, I mean, that was probably there the whole time, actually. So actually, maybe the best thing to do is just protect instantly. Just protect it. Now, there are 2 types of protections. One of them, obviously, is the what's shown, right? It's the acyl chloride. You can also do this one here on phenols. You can do NaOH CH3I. That makes a methoxy anisole. You get rid of that with HI. So you use base to add it. You use acid to take it off. So do whatever you need to do. That's just how it works. Okay. But because of the way the problem's written, we will go with this here. Pyridine is a good way. I don't know if you guys noticed that in that first problem. Pyridine is a good way to tell if they want you to do the acylation or the on the carbon or acylation on the oxygen. Yeah, so that's a good way to tell. But anyways, we'll get this here. And then again, you know, you guys might look at this and think, well, maybe some of you guys might look at this and think, oh, you try to trick us, right? That is a carbon chain. So again, we can do Fredo crafts here. And you might think, okay, let's just do you know, what you wanted me to do was an alkylation. But when we look at this kind of carbon here, right, that's a linear carbon, not a branching carbon. And so linear carbons, remember, the axis of this is acylation. Because remember, if I have a chloride like this is going to instantly rearrange. Like this is going to just do that. So in fact, what we get instead is this here, this cation here. So because of that, because it's not branching, we want to do an acylation here. And so you guys might think, okay, let's just go ahead and do acylation just straight up. So you thought you could trick us, but you couldn't. So you might end up doing something like this. But remember that whenever we're in synthesis, assume that para is major. So in fact, actually, if I did this, it would go here, which now destroys my synthesis. Okay. So what do I do to promote ortho attack? Well, if para is major, then we want to put a group that blocks the para that we can take off later. That would be sulfonation. I'm just going to put S here just because I'm lazy. Okay. And now we can do our acylation. Not pyridine, sorry, FeCl3. Don't forget, you need your H+ workup afterwards, otherwise your points will be massacred. So that we get this here. And then it's totally up to you how you want to do this here. But you can, I mean, you have to draw, it depends on who you draw first or which one you do first. But I would personally do the hydrolysis first. Okay. To do that. And then I would do the zinc HCl. Okay. what that will give you. Actually, this step here will actually get rid of the ester now that I think about it. It's actually undo the ester, but I don't think you're taught that. So you might be able to ignore that. But it'll depend on who you do first, right? If you hydrolyze off the sulfur first, or if you reduce off the ketone. It's up to you. Cool. All right. So that's that instance there. So that was pretty simple. Just wanted to get that concept out. Looking at this up here, we have a cyclopentane. Again, the bare bones of the molecule. And then we have, looks like an elongated diene. We added carbons. Only one way to do that, right? That's Grignard. So we can assume at the very least that this here is our original. So the rest of the stuff here is probably added in some kind of Grignard. Remember, Grignards require alcohols. So we probably did some kind of dehydration here. Right, where on that new carbon chain there was this alcohol, and then I can go ahead and cut this on that new carbon chain and say, again, if I put a marker where I cut, right, that's right next to the oxygen, so this is clearly a carbonyl that I added in. And what I have in its place, oh, sorry, I forgot this alkene here, is this here, which will be like my Li or my Grignard or whatever. Grignards you make from bromides, right? And this is an allyl bromide. Actually, we actually don't have to do this actually, because so I could go this route. I could totally go this route actually. This would work. But when you draw the from here, right, this is just an allylic bromide. So you're just saying that this was an allyl radical addition, and then from here it's just a matter of forming bromide. So this could work, right? This will get you, if not full points, at least the most partial credit, right? And you could always argue. So NBS HV, right, and then some small base, right, and then this is just like NBS HV again. I guess the only issue is this step here, because again, if you're thinking about where the radical would form, it's probably never going to form on this end here. So that's the tricky part of this, but you could get away with it. You could say you could argue thermodynamics probably, if you had to draw on this, but you can also just go from here to here, right? Because remember, anions just like to be less up anyways. So you could go ahead and just use NBUE here, just like we did earlier, and then just get straight to there. So you wouldn't even have to worry about that whole selectivity issue. Cool. All right. Nothing too crazy there, right? I guess the only thing that you could do here now is then do some kind of like 1-2 or 1-4 addition. But that would be a little hard to see, right? Cool. Okay. So that's the syntheses. Oh, I think I remember what I wanted to talk about. I don't know why I thought about this during that, but I mentioned dienes. There's a couple ways to make dienes, right? This is good to know, right? We make them from from this here, right? Elimination just like that. Kind of the popular route as of right now has been like the sort of organometallic into an alcohol into like a dehydration, right? That's kind of what we've been doing for a bit now. So let's even expand this. We can even do something like this, right? Or let's say that I introduce like a alkyne, right? Or I introduce like an alkene, right? Via Grignard. You could do that too, right? So rather than starting from the Grignard, you can start from the carbonyl, introduce these components as well, and do your dehydrations. That could also work. Alkyne might be the easier one, or it might be the better one to think about because it's a better Grignard, right? That could just go to like this. And then you could do like a selective reduction. Something like that, right? So just ways of making dienes, just possibilities, things to think about. Okay. Damn, another thing just escaped me. Like I wanted to say something and it just escaped me. What in the world? I don't know. I'm just going crazy, I guess. Cool. If I remember, I'll just mention it, right? I will probably won't though. Cool. All right. This one's a little bit harder, this benzene problem. Again, if I do DOU, 9 times 2, 18 plus 2, 20. Minus 1 is 19. Minus 9 is 10. 10 divided by 2 is 5. 5 degrees. We see the barcode, so it's 4 of those are benzene. Yeah, so 4 of those are benzene. When I look over here, I have a line about 200. So my question is this going to be a ketone or an aldehyde? I see that line at 10. I see a singlet at 10. So I know this is an aldehyde with 0 neighbors here. So actually, I'm actually going to just go ahead and put on the benzene because it's a great way of having 0 neighbors. Okay. When I look at the benzene situation, though, there's only 3 hydrogens and they're all singlets. So this is going to be a trisub. Couple ways of doing trisub. You can do something like this, where all the hydrogens are neighboring each other. So probably not that because these are singlets. I can do this where they are kind of, there's one guy that's a singlet and the other 2 are kind of neighboring, but right, there's singlets, right? So they shouldn't be neighboring at all. It just takes a while to figure out that it looks like this, right? This is like the canonical, like, hey, 3 things next to each other. No neighbors. So there's gonna be 2 other things here. I have looks like a bromine and 2 oxygens. So I have another oxygen here. But what are the bets that the oxygen has this next to it? So we have an oxygen, 2H quartet, 3S triplet. Nothing else at 4, so probably 0 neighbors here. So I'm gonna go ahead and put that there, and that at least leaves a bromine. Doesn't matter how these are oriented, right? It's always gonna be the same. Cool. All right. So there we have it. Those are the 2 midterms in their material. I'll write out the key for the 3rd one right now and send it out. And I'll fix the 2nd one, like that mistake. I think I made a mistake up here, right? On one of these. I think it was this one. Cool. I'm trying to give me like 1 minute. I'm trying to think what was it that I wanted to say here? Don't know. Maybe I wanted to say they could do a Diels-Alder, maybe. Maybe that's what I wanted to say. Oh, I remember now. I remember what it was I wanted to say. Okay, so back on this midterm. So last midterm, a big thing that tripped people up was the whole make everything from the same carbon, right? Same carbon reagent. That kind of tripped people up. You can actually do that here. If this target were not this, but instead we're sorry, they were this. Yeah, this could have been it. So how this would work? So we already know that we cut here. This, and then this would be this here, right? So remember it's trans, so this is gonna be trans here like that. So this is possible. So the question becomes then, how do we make this guy from the starting material? Because we know how to make this. We just went through that. That's just NBS eliminate, NBS eliminate, right? So that's not too hard. How do we make this guy? Well, again, we have to think in terms of allylics. So we have here a pi bond where there's an allylic ketone, and hopefully, you guys remember you can oxidize allylic alcohols using MnO2. So we could have had something like this. Okay. And so this alcohol could have been the result of, like, I don't know, like a water addition, right, to some kind of bromide, right? And then again, we know how to make the allylic bromide, so that shouldn't surprise anyone how we do that. Okay. So totally possible to make the ketone here from that. So don't forget that. That's what I wanted to mention. That was that was on the back of my head, because I remember someone asking about that. Is there a way to do that same thing where we make everything from the same carbon reagent? And we can. Cool. All right. That's it. I don't think I made any mistakes.